Hey guys, Adam here. With fall semester coming to an end, I've had many final projects going on. One of the classes I'm taking, Chemistry of the Environment, has got us doing a comprehensive analysis on whatever topic our group finds interesting. For my group specifically, we're taking a look at bioplastics, what could hopefully replace these guys right here. And now, plastics are a really big issue in our modern society, with these kind of miracle workers getting a lot of things done for us, but also posing a big environmental threat. With that, we're going to be looking at some of the biological-based solutions in place. Anyways, I hope you guys learn a thing or two about the science surrounding plastics. And yeah, enjoy! So welcome one, welcome all to the presentation about biodegradable plastics, an analysis from Adam Bede, Delaxan Mail Vagnam, Marissa Curry, and Zachary Gertain. Delaxan, take it away.
Before we dive deep into understanding the concepts involving biodegradable plastics, we'll first look at what plastics are in general. Plastics are synthetic materials made from a wide range of organic polymers such as polyethylene, nylon, and many other substances. Polyvinyl chloride is another polymer used in the synthesis of plastics, which was first polymerized between 1838 and 1872. But the first breakthrough came in 1907 when the Belgian-American chemist named Leo Becquerel invented Becquerite, the first real synthetic, mass-produced plastic. Plastics of all types, for the most part, share similar properties. They all tend to have low melting points, explaining why they're so malleable. They're also electrically and thermally insulative. They have a fairly good impact resistance, and they also involve in low costs when it comes to production. There are many different types of plastics that are produced and manufactured around the world today. In this slide, you see some of the most common types of plastics. Polystyrene plastics are plastics composed of liquid styrene. In foamed form, it is called styrofoam, and we use this for thermal insulation purposes. When it is not foamed, it has a shiny glass-like surface which we use for CD cases. Other uses include packaging materials and casings for electrical appliances. Polyvinyl chloride is another type of plastic that is used for insulation as well, and one that has a high fire resistance, making it a great material for the building industries. Polyethylene plastics are plastics that compose plastic bags, wrapping foils, and cable coverings. Polyurethane are plastics that you would see in mattresses, car seats, and in kitchen sponges. And lastly, you have polypropylene, which are plastics that you have in food packaging, automotive parts, and also plastic bags. All of these types of plastics that I just mentioned right now originate from crude oils and fossil fuels. But biodegradable plastics is the only type out of these plastics that does not come from a non-renewable source. Biodegradable plastics are composed of three main types of plastics called PLA, PHA, and starch blends. PLA is composed of sugar from corn and or sugarcane plants. Its building blocks or monomers can either be lactic acid or lactide monomers. These monomers will later be polymerized to form PLA plastics. PLA plastics are mainly used in the packaging industry, making use of these plastics to make cups, lids, cutlery, and straws. PHA are plastics that are engineered from microorganisms. PHA is more specifically produced in the cells of bacteria, which are harvested to obtain this compound and synthesized to form plastic. Similar to the MLA plastics, PHA plastics are used for single-use products such as food packaging, straws, and cutlery. Adam will go into further detail about how PHA and PLA are synthesized.
So here it is, the synthetic overview, taking a look at both PHA and PLA plastics at the smallest scale, their monomer building blocks. These blocks you see on screen can be repeated at the end location for short, medium, and long length chains, with the longer chains being the hardest to synthesize. The location of the methyl group in both cases can be modified to change various properties of the plastic, such as its strength, elasticity, and such. I am fortunate that my uncle owns a bioplastics company, and as he says,
So, there's like 300 different varieties of PHAs, and so depending on what you want to use it for, you can use one or the other.
But it's all about that R group. It's just that R group.
It's actually both. It's the R and the N, right?
Right.
So the PHB, which basically just has methyl on the R group, that is more of a structural molecule. So if you want to make a solid plastic or something.
Right.
Whereas if you want to, so we have some longer chain length PHAs, which are more elastomeric or more rubbery in consistency.
Yeah. Okay.
You can use those for more flexible plastics or for adhesives or for coatings or things like that, right?
Otherwise, these two types of bioplastics alone are quite distinct from one another when you look at how they're synthesized and how they decompose, which I will elaborate on starting with PLA. So what we have here is the production of PLA and its manufacturing mechanism. The initial carbon source is lactic acid, derived from fermenting the sugars of corn syrup and sugarcane plants. The systems used to process these carbon sources are quite similar to those used already for oil-based plastics. Of course, rather than oils, in this case we're using lactic acid and natural carbon sources. This system is an efficient process involving water pumps, reactors, and very high temperatures. This gathers high yields of PLA from the source carbon put in, upwards of 95% depending on manufacturing efficiency from start to finish. On a chemical level, the synthesis of PLA involves two sources: the ring opening of cyclic diester lactide and lactic acid, while being dissolved in a metal catalyst. This brings about a racemic mixture, which is then condensed at less than 200 degrees Celsius. This brings about the PLA monomers, where water is then removed to complete the final step of polycondensation, as you can see right here, into a longer chain. Following this, when you get multiple of these PLA chains overlaid on top of each other, they interact, making the structure at the foundational level for the PLA plastic material. Now on the flip side, engineered from microorganisms, we have PHA plastics. Caprivitis necator is one of the microbacteria fed to grow rapidly at the initial stages. They are fed with all sorts of carbon sources originating from agricultural waste. Once these microorganisms reach a sizable population, they're fed in deficient ways, reducing certain nutrients, which stresses them out and forcing them to synthesize PHA. The microbacteria are filtered and dried a few times to complete the process. Notably, compared to PLAs, PHAs are grown in varying yields of up to 80% of the organism's dry weight in the finished product. From a chemical standpoint, you can see this involves the metabolic cycles inside the microbacteria cell body to grow and synthesize PHA from its fatty and nucleic acids. The image in the top right shows a biological approach to cell growth, but more importantly, the synthetic scheme here in the middle shows the inner workings on a chemical basis. Nutrients are taken through fatty acid synthesis and oxidation and other processes to grow the microbacteria, which then synthesizes PHA in response to deficiency conditions. Here you can see the structure at the end of PHA, which again forms long chains which interact with one another, forming the foundational basis of PHA plastics. Now, here we come to an important point, which is looking at the degradation processes. After all, this is all the efforts of synthesizing efficient plastic being really put to use now. After the plastic has been used and disposed of, the important thing is that the material can be broken down into its substituent molecules. The decomposition process of PLA and PHA plastics are far better than current oil-based solutions. Most notably, PHA plastics surpass PLA in their ability to decompose via microbial enzymes. Just looking at the substrate alone, there's more room in PHA plastics for interactions to occur within the carbon chain, unlike PLA, which is slightly sterically hindered with its placement of the methyl and oxygen groups. As such, in the case of PHAs, microorganisms can easily enter, break down PHA, and use the organic acid as a food source to keep them working hard. PLA plastics, on the other hand, involve a slower and abiotic process to decompose via hydrolysis. Additionally, you have thermal degradation via heat and humidity, and you also have photodegradation from UV light. Although the chemistry may seem laborious, this gives an illustration of why an effective degradation method is needed for bioplastics, as Zach will further explain.
As we know, there is a lot of plastic debris in the oceans, and this plastic has caused damage to many ecosystems and animals. According to a study done by the University of Plymouth, over 260 species have been affected by plastic, resulting in impaired movement and feeding, reduced reproductive output, and even death. These animals that have been affected are not only affected by large pieces of plastic, but by very small pieces of plastic as well. The same study found that plastic fragments as small as 1.6 micrometers have been identified in some marine habitats. This is an issue because these microplastics can move through the food chain, meaning that the plastics ingested by smaller creatures can eventually move up the food chain into our diets. So how is biodegradable plastics going to fix these issues? Well, to clarify, biodegradable plastics can't fix the amount of plastic that is already affecting the ocean, but it can stop us from making the amount of plastic in the ocean worse. For starters, only 9% of plastic is recycled, while the rest ends up in landfills. Normal plastic can spend 100+ years breaking down and taking up a lot of space. But some biodegradable plastics, such as PHA, can break down over a couple months, which could relieve stress on the waste stream. Moreover, biodegradable plastics such as PLA plastics do not produce toxic fumes if they are incinerated and not put in landfills. But we are not done yet. Biodegradable plastics don't only solve our waste, they are better for manufacturing too. Biodegradable plastics can represent a significant energy savings. For example, the corn-based plastic polymer PLA uses 65% less energy than creating a similar polymer from raw petroleum. In addition, it produces 68% fewer greenhouse gases while manufacturing it, which can represent a significant environmental benefit. Not only is it better to produce, but it also helps with the issue of running out of fossil fuels, because biodegradable plastics such as PLA are made from corn, a resource that can be renewed annually. So, let's just switch to biodegradable plastic, you might say. Well, it's not that simple. There are downsides to biodegradable plastics. For starters, biodegradable plastics cannot decompose in landfills. Many of them need to be incinerated at a facility because it can be worse for the environment when they are not incinerated. In addition, they can cause issues in the recycling process when they are not sorted properly from other types of plastic because they are classified as a number 7 plastic, while most other plastics are classified as a 1 to 6. Lastly, some people argue while the corn used to create PLA is renewable resource, many people point out that the fields used to grow these crops could be used to create food for the world's growing population. Now on to Marissa.
So as Zach just mentioned, PLA and PHA plastics can be thrown into landfills. Although as biodegradable plastics, these materials deserve a much better end-of-life destination than a waste mountain or worse, the ocean. So how does the province of Quebec deal with this reality? Well, it turns out that we actually have a long way to go. So as you're all most likely aware of, Montreal does have a composting system where we're encouraged to place compost in the brown bins. One of the biggest composting plants can actually be found in St. Henry, which is essentially consisted of large piles of soil treated outdoors. But unfortunately, these materials are limited to types of compost that can be degraded under traditional quote-unquote backyard conditions, meaning that moderate temperatures are maintained rather than the high temperatures needed to degrade most biodegradable plastics. Many composters actually regard PLA and PHA plastics as a contaminant in these traditional sites because the compost can contain undecomposed plastic residues when being sold to potential buyers. Because of this reality, the City of Montreal currently does not actually have any way to compost biodegradable plastics, leaving them destined for the garbage, leaving their original purpose, which is to reduce garbage, unfulfilled. So what are our future plans to improve our system regionally? So it turns out that with Montreal's simple current composting system in place, overall residual waste has actually gone down 8% since 2010, which is not bad. Although 55% of what's currently going into landfills is made up of organic material that could potentially be composted. So Montreal announced its awareness on the matter, and in 2019, the City of Montreal was said to approve the $175 million plan, which actually rose to $589 million for the construction of our first industrial compost plant for St. Laurent Borough. It was announced that the plant, if everything went as planned, would be fully constructed by September 2021, but unfortunately the City of Montreal has not really spoken of the matter since. So in fact, other Canadian cities are actually further along in this process than Montreal. So a good example of proper disposal of biodegradable plastics is in Calgary, having the largest industrial composting facility in Canada that handles all sorts of compost, including biodegradable plastics. Many European countries provide examples as well for better processing of waste. So Germany in particular is an interesting example of the disposal of PLA plastics, allowing them to be thrown into recycling. According to the information published by German Ministry of Food and Agriculture, Germany actually has a system that successfully separates PLA plastics from other recycled materials using common near-infrared spectroscopy and allowing for PLA plastics to be recycled in a separate plant. So globally, the fundamental problem with this goal is the large cost of sorting systems or industrial plants necessary for disposal, and of course the energy and money put into the proper planning and execution of these plants. Although we must ask ourselves an important question: what's more important to us, our economy or the well-being of our planet? So now I'm going to pass you guys on to Adam.
Now, overall, we gotta look at what is the future of bioplastics. Notably, what bioplastics aim to do is remove the current issue of mining for oils and taking these underground carbon sources to the surface. These practices can be replaced with obtaining carbon sources from plant growth in the case of PLA plastics, or microbial growth and fermentation in the case of PHA plastics. These new types of plastics bring better practices for cycling carbon already in our troposphere. From the standpoint of how close we are to their full introduction, banning single-use plastics is something already happening on a national scale in Canada, and alternative types of plastics will be crucial for ecological solutions in places where they are most needed, such as hospitals, or like right now, during a pandemic, where a virus can be accumulating on most day-to-day surfaces. As such, there's a high demand for single-use plastics which can be disposed. Overall, this field of research among PLA and PHA plastics is young, and more work will be needed, notably for PHA, to pose a promising biodegradable future for our problem with plastics.
So those are the actual freeze-dried bacteria that we're using, right?
Really?
And then out of that, you get this kind of a powder when it comes out of purification.
When it comes out of what?
When it comes out of the process.
Okay, yeah, so that's kind of like the before and after.
Yeah, so this is just before the package. You get your little PHA molecules.
Mm-hmm.
So that's what that
Wow.
is. Here's some, Lego pieces.
There you go, wow. All right, the Lego brick, nice.
We've got some
The eco-friendly one.
the eco-friendly one. Here's some early attempts at making a frog.
All right, that's good. Well, that was all with the 3D printer then, eh? Or...
That was on the 3D printer.
Okay.
And then this was done through injection molding. So this is a cup that we were able to make.
Nice. Well, there you go. So I see that it's pretty rigid, eh? Well, it's still
Yeah. And then you can. So this has an additive in it. And sometimes what you do, because PHAs are expensive to make, right?
Yeah.
Just because we don't have a production facility in the world anywhere that's the same size as a polyethylene cracker. Okay.
Oh, definitely not. Yeah.
And so there's the scale challenge, but there's also the challenge that every gram of carbon that goes into the process, only a third or a half of that.
Yeah, well, that's it.
As plastic, right? Because the bacteria have to. Well, there's two things. The bacteria consume some of the carbon, and the other thing is that CO2 goes off when you go through fermentation. Sort of like when we breathe, we give off CO2. It's a way of the organism cleansing itself of oxygen, right?
Right.
If you have too much oxygen, that's toxic for you. So anyhow, so those are some of the things that we can make, and then we can make some nice films. So this is one of our examples of a film that we can make.
Okay. Wow. Yeah.
So we do stuff like that. When we can make netting bags, we can make and again, depending on what kind of end use you want, you can make thicker film, thinner film. You can make it with color. We have some antimicrobial additive that we can also put in there to give it more of an antimicrobial feel. You know, so there's different kinds of outputs you can get.
Interesting, yeah, for sure. Just anything like plastic wrap.
Yeah, yeah.
All right, nice. Wow.